All right, welcome back to 5.4. We're looking at ambiguous case for oblique triangles today. We're doing something different today. Okay, so as you can see, I have a split screen going on here. We are going to construct triangles. Okay, we're going to make some triangles and with given information, and we want to see if we can actually make a triangle or not, or sometimes maybe we can make more than one triangle. Okay, so you can see on my right here is the notes, and on the left this is Geogebra, and I'm using this program to help me to see if I can actually construct a triangle. So on the right and on the left, you will see here are two diagrams, right? They are identical. Okay, so well, they're not identical because I label them differently, but then they are identical with the size, right? You can see the angles are both 30 degrees. The side length here, A to B here is 10. This is also 10. Okay, so we have two identical diagram here. It says in triangle ABC, length AB is 10. Okay, so this is given. Okay, that's always the case. AB is always 10, and angle right now is going to be 30. Okay, so that's given. So now it says try to complete triangle ABC. So here's A, here's B. Presumably here is C. Obviously this C can move. It could be over here or it could be over here on the right. Okay, so again, this C is a point that we can actually change. Okay, but we want to build a triangle or construct a triangle with BC. So the side length of BC to be 4.5, 5, 6, 8, 10, and 10.5. Determine which length produces each triangle described in the fourth column. So here's the column, fourth column of the chart. Complete the chart, and you can see the first one has been completed. It says if the length of BC is 4.5, the value of BC divided by AB. So BC, remember, is 4.5. AB, recall, it was 10 centimeters. So 4.5 divided by 10 is 0.45. And we want to compare this value, BC over AB, we want to compare that value with sine of A. So really what we're doing, it has something to do with the sine, okay, which leads to sine law. And well, it does not lead to sine law, but it has something to do with sine law that we'll be looking at next lesson. Okay, so sine of A, so here's angle A, sine of 30 is 0.5. We can see that 0.5, the ratio of BC over AB, 0.45 is less than 0.5. And in that case, there's no triangles are possible. So I'll show you. So here on my left, I'm going to make a line of BC, given side length, that's this one. And I'm going to start from here, and I want the length to be 4.5. I'm going to type in 4.5. Oops, 4.5. Okay, so there is my BC. Or B, it's supposed to be BC, but it calls itself BG, that's okay. I'm gonna rotate this segment right here, and then I wanna see if I can make a triangle out of it, okay? So I'm gonna drag this, and I'm gonna rotate it, and you can see it doesn't quite touch the base. So you cannot actually make a triangle out of BC to be 4.5, okay? Out of this line, you can't make a triangle. And that's why it says no triangles are possible. Okay, now what we're gonna do is I'm gonna delete this line right here, and I'm gonna make a new length BC of 5. Now the ratio of BC over AB, this is gonna be 5 out of 10, which is 0.5. And now you can see the ratio of BC over AB, 0.5, is equal to sine of A, which we just calculated to be 0.5. Okay, sine of A is 0.5. If you put So sine of 30 is 0.5 if you put that into the calculator, or if you use your special triangle. It says if BC over AB is the same as sine of A, then we actually get one scaling triangle. And this, here I'll show you before I make the comment. So let's see, if we make this to be 5 as the side length for BC, and if we rotate this, okay, if we rotate this, you'll see it actually lands exactly on C. Okay, if you zoom in, okay, you can see it actually lands exactly at where C is. Okay, so it's actually on the line. So guess what kind of triangle this is? Okay, it's not only a scaling triangle, it's actually a right triangle. Okay, not only it's a scaling, it's also a right triangle. Okay, it's a special triangle. All right, it's a special scaling triangle, right? It's a special, it's a right triangle. Okay, so now I'm gonna delete again this line right here, and now I am gonna try. So actually, you know what? Never mind, because I see here it says one right triangle with c equal to 90. That's not where I'm gonna put it. This is 5 here, this is 5 out of 10, which is 0.5. 0.5 is equal to 0.5. It gives you exactly one right triangle with c equal to 90 degrees. Okay, so now I'm gonna make next one. Next line here, it says BC is 6. So I'm gonna put a 6 here for my side length. And right, that's right here. Is C is equal to 6, or BC is 6. Now I'm going to drag this line, and I want to see how many triangles actually I can make. So if I rotate this, you can see I can actually make a triangle right here. And if I keep rotating, I can actually make another triangle right here. Right? So when C, or when BC is 6, I'm going to put it right here. When BC over AB, this is 0.6. This ratio is actually bigger than sine of A. We actually end up with two scaling triangles. Okay, so when the ratio is greater than sine of A, we see that it has two scaling triangles. Okay, that's interesting, because I know if I make 8 as my BC, 8 divided by 10 is 0.8, and again 0.8 is clearly bigger than 0.5. We'll end up with two scaling triangles. And you know what, we're gonna, again, that's our hypothesis, so we're gonna try that. Okay, so I'm now gonna make BC to be 8, and oh, let's go, okay, right there, cancel, and I'm gonna drag this, and you can see I can make one triangle right here. If I keep rotating, I can make another triangle right there. So for sure, it does give us two scaling triangles. Okay, but now you think, okay, well, but then now if I put 10 in there, I would have 10 out of 10, right? So it could be here, oops, so it could be here, or it could be here, because this is going to be 10 out of 10, which is 1. And we know that 1 is bigger than 0.5 for sure. 1 is greater than 0.5. And now we want to see the description here. It says this is an isosceles, and this says this is one scaling. Well, then I guess clearly, if AB is equal to BC, then we have, well, it says right here, if AB is equal to BC, we would have an isosceles triangle, right? So let's see. I am going to, again, delete this, and I'm going to delete that. I'll delete this H as well. Okay, so now I'm going to make BC to be 10. Okay, so now again, I need to zoom in a little bit. And if I rotate this, you'll see we'll make a triangle right here. And we're going to keep rotating and see if we can make another triangle right there. It turns out that we can't, because then it's just the same line, right? It's both are equal to 10 for the length. So it's just going to be two overlapping lines. So that's not going to make us a triangle. So we actually can end up with one single triangle only. And this is an isosceles because AB is 10, BC is also 10. Okay, so this actually is going to be, we're going to fill that one in right here. Okay, so it's going to be this one right here because it's an isosceles. Okay, so now you might ask, okay, so then how do I tell? Because 1 is bigger than 0.5, then in that case, we end up with one triangle. But 0.6 and 0.8 both are also bigger than sine of A, but in this case, we actually end up with two scaling triangles. Okay, so here is the difference, okay? This is not only greater than sine of A, this is actually less than 1, okay? So we have 0.5 is less than 0.6, which is also less than 1. In that case, we actually end up with two triangles, right? This case, it was 0.8 was greater than 0.5, but 0.8 is less than 1. And again, it's between the ratio of BC over AB is between sine of A and 1. In that case, you end up with two scalings. When it's equal to 1, you will see you have one isosceles, because it makes sense, because BC over AB is 1. If that's the ratio, then that means two side lengths are the same. Therefore, you would have an isosceles. The last one, 10.5, if this was the length for BC, we have 10.5 over 10. And I have no idea what this is. I'm going to put that into a calculator. 10.5 divided by 10. This, oh, of course, this is 1.05. What am I talking about? 1.05. 1.05 is clearly bigger than 1. It actually, we are comparing with the sine of A. So this is definitely bigger than 0.5. So let's see what happens here, okay? So let's delete this BC here. I'm gonna get rid of that point as well. Okay, so now I'm gonna type in 10.5 for BC, like that. And now I'm gonna rotate this. You'll see we have one triangle right here, for sure. And I'm gonna keep rotating, and you'll see this is not only just overlapping, it actually can go all the way to the other side. Now you can see that it goes to the other side. Now you might say that, well, how come then it's not two triangles? How come it says it's one scaling? Well, it is because the angle A has to be 30, right? If you have BC on this side, then angle A is no longer 30. It's going to be 150 now, right? It's going to be this side of the angle, not on the right. So in this case, we would still have one scaling because angle A has to be on this side. Okay, so again, let me just zoom out a little bit. You'll see we can rotate this and we'll make one triangle right there. And I think we shouldn't just compare with sine of A, really we should also compare with 1. So this case, this is less than 1 and this is less than 1.05. This was the ratio of BC over AB. So whenever the ratio of BC over AB is greater than 1, we can only have one single triangle. Okay, that's one scaling triangle. Okay, yeah, that's it for this one. Here we have a note here, is that the ratio BC over AB is the ratio of length on the side opposite from angle A to the length of the side that is right next to angle A. Okay, so if it's BC over AB, this is always the length of the opposite side from angle A to the length that is right adjacent to angle A. Okay, so that's the criteria. Okay, now what I want you to do is I want you to maybe predict, see what happens with now instead of A being 30 degrees, we have A, well now I have beta here, but okay, it doesn't matter. A is 60 degrees, the setup is the same. You can see here's the angle A. I'm still making AB to be 60, or sorry, AB to be 10 centimeter. And now you need to pick the values of BC and to fill in this table. Okay, so I'll give you a try. Just try it, see what happens, okay? And I'll come back and show you. All right, so what we should do first, in my opinion, is that we should probably calculate and see what sine of 60 is, because we are really comparing with this ratio, right? Sine of 60 degrees, if you put that into a calculator, gives you 0.866. Okay, so now if we don't want, and we know that value of BC over AB, so we are making AB to be 10, so it's going to be something over 10, right? In this case, it's our EF. If we don't want to have any triangle, again, given this information from the previous example, we want the ratio to be less than sine of A. Okay, since we know sine of A is 0.866 and AB is 10, so as long as BC is less than 8.66, we are going to end up with no triangle. Okay, so you know what? Let's try it. Let's try to make length of BC to be 5, and let's see what happens. Okay, so that's 5 out of 10. The second one, it also says no triangle is possible. So in this case, I'm going to try 8 because it's kind of close to 8.66. So this is 0.5, this is 0.8. And we know that 0.5 is less than sine of A, again, because sine of A is 0.866. And we know that 0.8 is less than sine of A, okay? So now that's our prediction. now we're gonna try to verify that. Okay, so again, here is the triangle, or here's the partial triangle. We want to use AB, right here is 10, angle A is 60 degrees. We are gonna make BC to be 5 right now, and we want to see if we can actually make a triangle out of that. Okay, so length is 5, and now we're gonna rotate this. You can see clearly it's not gonna touch the base, so there's no triangle possible with length of 5, which again is what we predicted. Okay, so now we're gonna try 8 as length of BC and see what happens. 8. Okay. Oops, sorry. Let me change this first. Okay, now let's drag this. You can see it's almost touching the base, but not quite, right? You see that? And we still cannot make a triangle. Perfect. That's what we predicted. Okay. All right. Now let's see. How about the second scenario? We want to have 2 scaling triangles. Okay. So now, if we refer to the previous example, if we want to have 2 scaling triangles right here, that means the ratio has to be in between sine of A and 1. Okay, so let's see if that's the case here. So if we want the ratio between 0.866 and 1, so what we want is we want this to be in between. Oops. So this is sine of A. We want it to be between sine of A and 1. Okay, we want this to be the case. So now we need to pick some side length. So now I know the ratio is 0.866. I know 9 out of 10 is 0.9. So that's definitely going to work, right? I don't know. We'll see. And let's just try 9.5 as well, because this is going to be 0.95, which again is in between sine of A and 1. Okay, so now let's try to test our hypothesis and see if it's gonna work. I'm gonna delete all these points. Oh no, not F. Delete that. Okay, so now let's make BC to be 9. And let's rotate this and see what happens. So we'll see. We will touch the base right here once. So we can make a triangle. You can see there's one triangle right there. If we keep swinging this arm, you will see that we can make another triangle right there. So it does make sense. It does work, right? Our hypothesis was right. Okay, so now I'm going to delete this and I'm going to make another one. And I'll make this 9.5. And now we're going to swing this and then we'll see if it's going to work. So you'll see one triangle for sure. We will make another triangle right there. Perfect. This is awesome. Okay. Now, so again, so far, the pattern has been consistent with the previous example. Okay. Now, before we do these two, I'm going to look at this one, isosceles triangle. In the previous example, we can have one isosceles triangle if AB and BC are the same. I think this is going to be the same because obviously if AB and BC are the same, it's going to be an isosceles, right? This is just 1. Oops, ratio is just 1. Okay, ratio is 1, therefore it has to be isosceles because you would have 2 equal side length. Okay, so now here we have a description of the triangles. We have 2 of them here. I'm going to say one scaling and this one is a special scaling. This is a right triangle. Okay, right triangle is also a scaling. Okay, scaling, recall, is just that as long as you have 3 different side lengths, then it's a scaling. Okay, so right triangle is definitely, it could be, I shouldn't say definitely, it could be a scaling as well. It doesn't have to be scaling if it's a right triangle, because you could have 2 legs to be the same length. Okay, but anyways, we'll see. If we want to have a right triangle in the previous example, yeah, that's right, previous example here, it says, as long as the ratio is the same, right, 0.5 equal to 0.5. In that case, we would have a right triangle. Now, we know the ratio is 0.866. So, in order to, it's an approximate, right? It's not exactly 0.866, but close enough. I think we'll take that. So, in that case, we want length of BC to be 8.66 because 8.66 divided by 10 is 0.866. Okay, so that's what I'm going to do right now. I'm going to make BC to be 8.66 And I'm going to rotate this and see if that's the only triangle I can make. Because if it's a right triangle, it should land exactly on F. And you can see, I mean, I can zoom in, but you can see it's right on it. Okay, well, not quite, but I mean, I can adjust a little bit. You just have to trust that it's going to be right on it, because I can't, you know, pinpoint, right? So you just have to trust me. Okay, it's exactly right on C right there. Okay, so it does make a right triangle. So far everything, again, all the patterns has been consistent with the previous example. And the last one that I need to show you would be, how do we make one single scaling? Okay, and that's not a right triangle. So in the previous example, it says that we can have one scaling, and that's not a right triangle if the ratio of BC over AB is greater than 1. Okay, so now same thing. If I want the ratio to be greater than 1, then I just need to pick some length that's longer than BC. I'm going to make it like 15 this time, okay, just to make sure that it's big enough. So then you can see clearly it's only one triangle. Okay, so 1.5 is bigger than 1. Okay, so now let's see. Again, I'm going to make a triangle with BC to be 115 centimeter right here. Okay, I need to zoom this out here. Okay, oh, there we go. So if I rotate this arm, you'll see we can definitely make a triangle right here, right? But if I swing this to the other side of the angle A, you can see we actually are not going to make a triangle. It's going to swing all the way to this side. And again, this triangle doesn't count because in this triangle, angle A is no longer 60, right? 60 degrees on this side. If you're saying this is a triangle, then this angle is actually not 120. Okay, so that it doesn't really count. Okay, so it only counts if it's on this side, because on this side, angle A is still 60 degrees. Okay, so let's summarize this. I think we are pretty certain now, because of these two examples, we can probably summarize this with this table right here. It says complete this chart to summarize the result. Place a check mark at the appropriate box. Okay, so no triangle. Again, that's when BC over AB is less than sine of A. Again, recall BC is simply the side length opposite from angle A. AB is the side length that is next to the angle A. Okay. If the ratio of BC over AB is less than sine A, there's no triangle possible. Again, we can show from the previous example that we just did, again there, and the previous one, we can have a right triangle if the ratio is exactly equal to sine of A. Okay, we will get an isosceles triangle if the ratio is exactly 1, which makes sense, right? Because then that means BC is equal to AB. So 2 equal side length is one isosceles triangle. We'll get one scaling triangle that's not a right triangle if the ratio is bigger than 1. And this is not, oops. Oh, not a right triangle. Okay, it's not a right triangle. We would have the ratio bigger than 1. And finally, we will get two scaling triangles if the ratio is between sine of A and less than 1. And this is important because if the diagram is not given and it only tells us the ratio, or it just tells us the length of BC, really we don't know which triangle it's talking about, right? Let me show you what I mean. Okay, so let me delete this arm right here. Let me make this 9. So we would have two triangles. So if the question is given to us where it says AB is 10, BC is 9, and angle A is 60 degrees, we actually don't know which triangle it's talking about. It could be referring to this triangle, or it could be referring to that triangle, right? So we don't know which triangle it's talking about, and that's why it's ambiguous, right? And that's what the lesson is. It's the ambiguous case for oblique triangles, right? We don't know which triangle we're talking about here. Okay, we don't know which triangle we're talking about. Okay, so there you go. That's the lesson for today. It really just depends on what information is given to us, and we can tell whether we can make a triangle, 2 triangles, no triangle at all, 1 isosceles triangle, or 1 right triangle. Again, here is the summary. This is the summary of how to tell. Okay? Now you can do some practice questions and let me know if you need help. Good luck!